Okay, so here we are. We're going to finish Chapter 7, Section 7.10, and this is called the Wilcoxon-MannWhitney Test. How do you spell Whitney? Okay. The Wilcoxon-MannWhitney test is used when you have a numeric variable, you have two independent samples, okay. So far it looks like the same situation as a t-test for independent groups, okay. But the key here is that we do not use the central limit theorem to assume that the sampling distribution is normal. Okay, so do you guys remember the conditions that were necessary in order for us to apply the central limit theorem? Yeah, so we have, so just a review here. Conditions to use the central limit theorem. We said that the samples had to be randomly selected. Samples are randomly and independently selected. Then we said the samples are not too big and the samples are not too small. So sample not too big, so not more than 10% of the population. And we said samples are not too small. Okay, I hope this is kind of familiar. Yes, maybe? Okay. And do you remember what samples not too small entailed? Okay, so we said if n is greater than or equal to 25 or 30, that's big enough for most scenarios, okay? Or if the population is normal, or at least unimodal and symmetric, okay, then any size n is fine. Any size n is big enough, okay? So this was, let me just put a box around this to remind us that this was a review of the conditions necessary to use the central limit theorem, okay? And the central limit theorem said that the sampling distribution follows a normal distribution, and because of that we can then use the t-distribution in our t-tests, and all of that stuff is all based on that, okay? And this is the key distinction with the Wilcoxon-MannWhitney test, is that here we are not using the central limit theorem, okay? So the most common scenario for using and I'm going to just abbreviate this, the WMW test. Okay, so the most common scenario for using the Wilcoxon-MannWhitney test is you have two independent samples. Okay, both samples are, or at least one of the samples are small, but we'll just say both samples are small, and at least one sample has some outliers indicating that the population that it's coming from is not normal. Okay. So if you have this scenario where it's very clear that the population from which you're drawing a sample is not normal, then you'll want to apply the Wilcoxon-MannWhitney test, okay? Because in those scenarios, the conditions to use the central limit theorem no longer hold, and therefore you can't do the t-test, you can't do these other tests that we've learned, okay? Really just the t-test so far, okay? So the Wilcoxon-MannWhitney is in a family of what we call non-parametric tests. Okay, so non-parametric tests do not put assumptions on the populations. Okay, so that's in contrast to a t-test. A t-test where at some degree we're assuming that the sampling distribution follows the normal model or follows the normal distribution, and that and because the normal distribution has parameters mu and sigma defining it, those are called parametric tests. Wilcoxon-MannWhitney falls into a category or class called non-parametric tests, where you're not putting those types of assumptions on the population. Okay, and so this is probably the most common scenario, where you have two samples that are small, okay, and at least one of those samples has some major outliers indicating that the population is not normal, and then that way you don't want to use the t-test. Okay, it would be wrong to use the t-test. Okay, so just an aside, you can there's a whole branch of statistics dedicated to non-parametric tests. Okay, you can take an entire course on the non-parametric statistics. You can dedicate your life studying the thing. This is going to be our only exposure to non-parametric statistics. We're just going to learn this one test. We're going to spend maybe half an hour on it, and that will be it. Okay, so you're just getting a small taste of non-parametric statistics or non-parametric tests with this one Wilcoxon-MannWhitney test. Okay. Another note is that if you were to take another statistics class in the future, or take some other, I don't know, research methods or something type of class like that, they might call this the Wilcoxon rank sum test. Okay, so same Wilcoxon. It could be also known as the Wilcoxon rank sum test. Okay, the Wilcoxon rank sum test when you go through it, looks completely different. Okay, the everything about it looks different, but it turns out that the conclusions made from the Wilcoxon rank sum test will match up with the conclusions from the Wilcoxon-MannWhitney test. Okay, the underlying math behind it ends up being the same. Okay, so even though the methods behind them are different, they're basically used for the same thing. Okay, they're used to see if the populations are different. Okay, let me say that. Stats 13, March 5th, slide 1. Okay, so we're still doing hypothesis testing here. Okay, but the hypotheses are written in slightly an odd fashion here. Okay, or it just feels a little bit clunky, because again, we don't have parameters. Okay, so remember, these are non-parametric tests, or this is a non-parametric test, and so we cannot use, we do not use mu in anywhere in the hypotheses. Okay. Okay, because mu is a parameter of the population, so we're not using mu. Okay, it's a non-parametric test, Wilcoxon-MannWhitney. So what we would say is that the null hypothesis is that the population from which sample 1 is drawn has the same distribution as the population from which sample 2 is drawn. Okay, so that it feels a little clunky, but that's really the only way we can say it without using any kind of mathematical symbols, because here again we're not using any kind of parameters. So the null hypothesis says that, you know, you drew 2 samples and they're essentially coming from the same population, or if they're if you have 2 different populations, at least the distribution of those 2 populations are the same. And then the alternative is that the population has a different distribution. Okay. So let me just write the non-directional alternative would be that, you know, the populations have different distributions. Okay, or you could have a directional alternative. And that would be, you know, the population from which sample 1 is drawn tends to produce values that are larger or smaller, if you have the other direction, than the population from which sample 2 is drawn. Okay. So here we're again trying to make statements about the population without making without referring to any kind of parameters in of themselves. So what we're limited to saying is that the population from which sample 1 is drawn tends to produce values that are larger than the population from which sample 2 is drawn. Okay, again, it sounds very clunky, but without the shortcuts of using mu or things like that, that's what we're limited to. Okay, and again, we're talking about the distribution of the populations, because of course when you look at any individual value, one might be larger or smaller regardless of what the population looks like. But again, we're making statements about the overall populations. Okay. Just another note is that in general, non-parametric tests are less powerful than their parametric counterparts. Yeah, so I'm going to talk about that right now. Then there. Okay, so in statistics we have a definition for the word power. Okay, when we talk about the power of a test, this is equal to 1 minus beta. Do you guys remember what beta was? So alpha is your significance level. And alpha is equal to the probability of committing what? What kind of error? Alpha is equal to the probability of a type 1 error. Okay. Beta, on the other hand, is equal to the probability of what? Committing a type 2 error. So what is 1 minus beta? No, it's not alpha. Whenever you have 1 minus the probability, that is the complement. So power is the complement of a type 2 error. Okay, so power is equal to the complement of a type 2 error. What was a type 2 error? So type 2 error is, let's just write this. Our decision was we did not reject the null. When, what? We didn't reject the null, but we should have, right? Because when the null is false. So type 2 error is we did not reject the null when the null is false. Okay, so what would the complement of that be? So the complement is we just get rid of this word not, okay? And it becomes we do reject the null when the null is false. Okay, so the power of a test is the probability of we do reject the null when the null is false. Okay, so power is a good thing. High power means whenever the null is false, you have a high probability of rejecting the null. Okay, and that can be accomplished by increasing your alpha or making your test better or whatever, gathering more data, or there's just the properties inherent to the test. Okay, and so when I say in general non-parametric tests are less powerful than their parametric counterparts, okay, just imagine two scenarios. You have the same data, and the null, in truth, the reality is that the null is false. Okay, if you were to run a parametric test on that data, you have a higher chance of rejecting the null than with the non-parametric test. Non-parametric test, you might come to the conclusion we don't have enough evidence, whereas with the parametric test, you would say we've got enough evidence to reject the null. Okay, non-parametric test generally, because you're putting less assumptions about the population, it generally takes more data for you to make a reasonable conclusion, or to make a conclusion where you're going to reject the null hypothesis. Because you're putting less assumptions about the you're putting less assumptions on the distribution of the population. Okay, so in general, if you're in a situation where you can use the t-test, use the t-test. Okay, the t-test is more powerful than the Wilcoxon-MannWhitney test. But if you have a situation where it is wrong to assume that the t-test, assume that the central limit theorem holds, then you have to use the Wilcoxon-MannWhitney test. Okay, so if these conditions are not met, you've got to use the Wilcoxon-MannWhitney test. Okay, so let's try an example. We'll walk through solving, doing a problem with the Wilcoxon-MannWhitney test. Okay, so here we have gone to the forest and we've gathered some soil respiration data. And I'm not, I don't know anything about ecology or anything like that. But basically, we went to two sections of the forest. there is a section where there is growth, okay, lots of growth, and then there's a section where there is a gap in the growth, okay? And what we did is we took measurements and we measured soil respiration, which is apparently how much like carbon dioxide it gives off per gram of soil in an hour. Okay, per gram of soil in an hour. This is how it's measured. So we measure how much carbon dioxide the soil breathes. Okay, and this is the data that we've gathered. Okay, make sure when you're writing your data, you leave a little a column to the left and to the right of what you do. Okay, so we're going to put the data in order from least to greatest for both of these things. We have 1, 2, 3, 4, 5, 6, 7 measurements from the growth section and from the gap section. We have these measurements. Okay. And so we want to know, does the soil in the growth area give off more CO2 than in the gap area? And so from looking at our data, what would you say? Yes, it seems quite clear that the growth numbers tend to be larger than the gap numbers, but we'll carry through our test, okay? And so again, our null hypothesis is that the respective populations have the same distribution. And then the alternative hypothesis here would be that the population corresponding to the growth section or to the growth data tends to produce values larger than the population corresponding to the gap data. There we go. Again, we just have clunky alternative hypotheses. Okay, so again, step one, important that I didn't think, is just put the data in order from least to greatest. For both samples. Okay. So once you do that, then we can do the test. Okay. So what I'm going to do is I'm going to count for each number in the growth data. I'm going to count how many numbers in the gap data are smaller than this number. So my first number here is 17, and I'm going to go to the gap section, and I'm going to count how many numbers are smaller than 17. Okay, so I got this 1, 2, 3, 4, 5. I've got 5 numbers in the gap data that are smaller than 17. I do the same thing with 20. Okay, and I go 1, 2, 3, 4, 5, 6. 6 numbers in the gap section are smaller than 20. Okay, and I do the same thing for 22. Whenever you encounter a tie, those are worth 1/2. Okay, so I've got this 6 is smaller, 13, 14, 15, 16, 18. Those are all smaller. So I've got 6 numbers that are smaller, and I have a tie with 22. So I write 6.5. Okay. If there was another 22 in here, each of those would be worth 1/2. Okay. And so if there was another 22 in here, I would have 6 numbers that are smaller, and then a half and a half. So I would have a total of 7 over here. Okay. And the next number is 64, and then when we look at that, all 8 numbers are smaller, and these numbers over here, they're all bigger than 64, and so they too will also have 8 numbers that are smaller. Okay. So an interesting analogy between parametric tests and non-parametric tests is that parametric tests are like business and non-parametric tests are like sports, okay? In that in business, it matters whether you lost $1,000 or lost $1 million. Okay, it's a big difference between those two. But in sports, it only matters if you won or lost the game. It doesn't matter if it was a blowout or if you barely scraped by and beat them by 1 point at the end. It just matters whether you won or lost. Okay, and so with non-parametric tests, these numbers 64, 170, 190, and 315, they all contribute the same amount towards this thing that we're calculating. They all count as 8 points or 8 values in the gap that are smaller. Okay, so it doesn't matter that this is 315 and that's 64. This could be 3 million for all we care. It's just they're all bigger. Okay. We do the same thing on the other side. Okay, we look at the 6. How many numbers in the growth data are smaller than 6? 0. Okay, and we just go through and we do this for all of the bits of data. 18 has 1 number that's smaller. 22 has 2 and a tie, so we write 2.5, and then we have 3 numbers that are smaller than 29. Okay, so step 2 is for each value, count how many numbers in the small other column are smaller than the selected value. Okay, so then the next step is we just add up all of these numbers. So I do 8 plus 8 plus 8 plus 8 plus 6.5 plus 6 plus 5. I don't know what all of that is. I get 49.5. And over here, I add these up and I get 6.5. Add up those counts. Okay, and the larger of the 2 numbers will become our test statistic U. Okay. Okay, so in our case, U is equal to 49.5. All right, and at this point we just go to our reference tables and we look up the test statistic U and to get our corresponding p-value. Okay, And so here we have a designated table for the Wilcoxon-MannWhitney test, okay? Look up U in the reference table. Okay. Now when we go to our reference table, okay, it's table 6 here, there's two values here. There's an n and then there's an n prime. Okay? N and n prime correspond to the counts of our sample sizes. Okay? So the sample size of the growth data is n is equal to 1, 2, 3, 4, 5, 6, 7. And for the gap data, n is equal to 8. I've got 8 numbers in the gap data. Okay? So whichever is the larger sample size, that is your n, and the smaller sample size is your n prime. Okay? It doesn't matter whether the values are big or small in which one, it's just, in our case, we're going to use 8 for n, and then n prime is going to be 7. Okay, so just figure out your sample sizes. The larger sample size is n, the smaller sample size is n prime. Okay? Oops. Don't want this open here. Okay, so I'm going to, n is 8 and n prime is 7. Okay? And so here my test statistic is 49.5. Okay? And so the way our table works is we look at these bold print numbers. Okay? And if our test statistic was 48, the corresponding tail area would be 0.021. And if our test statistic was 50, our corresponding tail area would be 0.0093. So let me just put a little, because we've got n is 8 and n prime is 7. So essentially we have 49.5, which is between 48 and 50. So our corresponding tail area is between 0.021 and 0.0093. Okay, so U is equal to 49.5. So the tail area is going to be between 0.021 and 0.0093. But wait, if you read the top of our table, okay, it says the corresponding p-values for a non-directional alternative is in italics. Directional p-values are found by dividing the numbers in italics in half. Okay, so I know it's just the flip side for the t-table, but non-directional alternative p-values are given here. If you want a directional p-value, you take this number in italics and divide by half. So the question is, do we have a directional alternative, yes or no? Yes, we do, right? It says the population corresponding to the growth data tends to produce values larger than the population corresponding to the gap data. So we have a directional alternative. And so that means my p-value is going to be 0.0. I'm going to take each of these things and divide by 2. Okay, so I'm going to just write it down here. So the p-value is going to be between 0.021 divided by 2. So I do 0.021 over 2. So it's going to be less than 0.0105, but more than 0.093 divided by 2, 0.00465. Okay, so this is my p-value. So my p-value is basically between is less than 1% and more than 5 thousandths, I don't know, what, or 5 1,000ths, more than half of a percent. Okay, so our p-value is quite small, so we would reject the null hypothesis, and we would say soil from the growth sections produce more CO2 than soil in the gap sections. Okay. Is that all right? Working through the Wilcoxon-MannWhitney test. Yes?
How did you decide the p-value is small?
I didn't specify an alpha, but if alpha is not specified, let's just assume alpha is 5%. Okay? So if alpha is 0.05, my p-value is less than 0.01 and bigger than 0.00465. Okay, so my p-value is less than 0.05, so we'll just say it's small. We're going to reject the null hypothesis. Okay, so again, walking through doing the actual work behind the Wilcoxon-MannWhitney test is not incredibly challenging. Okay, it's a little tedious. You just count how many numbers in the other column are smaller than the current number, add those up, and you look it up in the table. Okay, and using the table is a little weird the first time you use it, but it's not so bad either. Okay, you just find these, and then sometimes you're going to get test statistics that are exactly 38 or 46 or whatever the bold number is, and then your corresponding p-value is going to be exactly that number. Okay. Again, the key here is knowing when you should use the Wilcoxon-MannWhitney test. Okay, and we use the Wilcoxon-MannWhitney test when it seems like you would want to use the t-test, but you cannot assume that it meets the central limit theorem conditions. Okay, so if it seems like, so if you have two independent samples and a numeric variable and you want to compare those samples, but the conditions for using the central limit theorem are not met, that is when you would use the Wilcoxon-MannWhitney test. Okay, and again, the most common scenario is you have a small sample with some obvious outliers, right, where you have at least one or two values that seem to be magnitude of order larger or smaller than the other values. Okay, usually most of the numbers are they seem like they're within a comparable range. Okay, then it's probably not a problem. But if you got one or two values in there that seem crazy large compared to everything else, that would be a good indication that your population is not normal, and just lost what I'm saying. That your population is not normal. You can't use the t-test. You have to use the Wilcoxon-MannWhitney test. Okay. I don't know if it's necessary that I explain the math behind where these values in the Wilcoxon-MannWhitney reference table are coming from. Okay. I guess you just suffice to say you can do a permutation of all, like if you have two teams, like a red team and a blue team, you can just do a random permutation of what are the possible finishes. Like if they have a race, okay, you can do permutation, and if it's completely random, usually you'll have, you know, it'll go like red, blue, blue, red, blue, something like that, okay? And you can calculate all of the basically these ranked differences if you just put these in order here. And if you can do a permutation for every single thing and then calculate the probability of each of those permutations, and you would get this table here. Okay. The book talks about it a little bit. It's I would not stress too much about it, okay? Just, I think the important thing is recognizing a situation where maybe a non-parametric test is better suited, okay? In Chapter 8, last week we covered just one section from Chapter 8, and that was the paired t-test. The remainder of Chapter 8 is all non-parametric tests for paired data, okay? I'm going to skip over those. If you, in your own personal research or whatever your professional career, you come across a situation where you've got paired data, but then it seems like you don't want to use the paired t-test because you're not sure if it meets the central limit theorem requirements, you can consult Chapter 8, and they list off non-parametric tests. There's a whole bunch of them for paired data. Okay, you've got the sign test and then the signed rank test. Also Wilcoxon. Wilcoxon did a bunch of this non-parametric stuff. So that's all the rest of Chapter 8. Again, I'm electing to skip over that, but I want you to know that it exists, and you can at least just flip through the section headings in Chapter 8, but you will not be tested on that or anything like that. So you're responsible for knowing Section 710, WilcoxmannWhitney Test. The other stuff from Chapter 8 is there for your enjoyment, and it's there. Okay, any questions? Okay, let's say that, and let me do it on time. Okay, so let me just start Chapter 9. Okay. Chapter 9, we're going to do, we're going to deal with categorical distributions, okay? Actually, we're going to cover both chapters 9 and 10. Feels like a lot, but it's actually, they're all relatable. So categorical variables, okay? So all of Chapter 7, and then all the t-tests, Wilcoxon-Mann-Whitney stuff, we were all dealing with numeric variables. And so now we're going to deal with categorical variables, okay? And so when we have categorical variables, you know, we're dealing with things like gender, race, or things that have a yes or no answer, okay? That doesn't mean that there's no numbers involved. It just means the individual response is a categorical response, okay? But when we summarize these categorical responses, we're going to have counts. And counts are going to be numbers, of course, okay? So the individual responses are counts, so keep that in mind. Individual responses, are categorical, okay? But the summary of our data will have counts. So it could just be as simple as, you know, in a classroom of 50 students, 28 are female and 22 are male. Okay? This is categorical data. The summary of our data will have counts. Okay? So just because you see numbers doesn't mean it's numeric. It's categorical data. Okay? And we also, another way to summarize categorical data is with the use of proportions. Okay? So proportions also summarize categorical data. So in our case, if we do p hat for female would equal 28 divided by 50, and I would have p hat is 0.56. Okay. So our first bit of inference using categorical variables will be to create a confidence interval for the population proportion P. Okay. So maybe you have a question, and when you ask something like, what percentage of RNs, so registered nurses, are female? Okay, this is a question. So you want to know, what you're going after is the population proportion P that are female in the population all RNs. Okay, so our population is all RNs, and the parameter of interest P is the proportion that is female. So you gather, somehow you obtain a random sample of, let's say, 80 nurses. Okay. And in your random sample, how many are female? I don't want to get in trouble, but I feel like it's still very much female, the profession. So 70 out of 80? I have no idea. Does that sound reasonable? Sure. Okay, so we'll say 70 are female. I have no idea. I should probably do a little research before I make up these examples here. But okay, so a random sample of 80 nurses, and in your sample 70 of them are female. Okay, so our proportion P hat is 70 over 80, and that's 0.875. Yeah, 0.875. Now, I want to take just a disclaimer, is that in our book, the book does something a little bit just non-standard. It's not wrong, it's just a little bit different from most other texts that I've encountered. And when it creates a confidence interval, it doesn't use the traditional sample proportion P hat, it uses something called the Wilson adjusted sample proportion, okay? And I can understand why, but it's P squiggle, P tilde right there. It uses the Wilson adjusted sample proportion, which is not going to be 70 over 80. It's, you take the count and you add 2, and you take the sample size and you add 4. So you're going to get 72 over 84 for P tilde. And so you get 0.857 rather than 0.875. Okay. And I've seen a bunch of different textbooks, and this is the only one that that I've encountered, at least at an introductory level, that uses this. The reason why is traditionally you would use P hat, and then you would create a standard error based on P hat. Okay, but you run into problems if you use p-hat, you run into problems if you're searching for a proportion of something that has a very small value. Okay, so let's say you wanted to know, what percentage of people have I don't know, some kind of rare disease. Okay, and so maybe you survey 200 people, and even after 200 people, none of the people you encountered had this rare disease. Okay, so your sample proportion is technically 0 out of 200. Okay, and in that case, your p-hat is 0, and then when you do your calculations for the standard error, you also get a 0. Okay, and so your confidence interval ends up being 0. There's no standard error. You run into some issues there. Okay, by using the Wilson adjusted sample proportion, it forces you to add 2 to your quote observed and 4 to the sample size. So if you looked at 200 people and you encountered no one with the disease, then your Wilson adjusted sample proportion would then change from 0 over 200 to be 2 over 204. Okay, so it gives you at least a non-zero value to work with, which will produce a standard error. Okay, and the flip side is also true. If you survey something where the overwhelming majority of people will answer yes, so I don't know, you survey 100 people and all 100 people say yes to whatever question it is that you're answering, again, in that case, your p-hat would be 1. It would be 100 over 100. But then the Wilson adjusted sample proportion would change that to 102 out of 104. Okay, so it pulls it away from 100% and brings it, it changes it a little bit. Okay, so just a little bit disclaimer. This is not many textbooks use this. Okay, this is a completely valid method and it's not wrong, but it's just not common. Because this is taught in the textbook, we'll just stick with what's taught in the textbook, okay? I'm not going to say learn this and learn all of these other things. We could do that if you wanted to, but so we'll just say use this, and I'll try to be clear to use your Wilson adjusted sample proportion p tilde, okay? All right, so anyway, we use this, and let's we're going to make a confidence interval. Make a confidence interval for p based on p tilde. Okay, so again, our data, we have 80 nurses, 70 are female. Is 70 plus 2 over 80 plus 4, and I already forgot what that was, 0.857. So our confidence interval, we say 95% confidence interval for p is going to be p tilde plus or minus 1.96 times our standard error. Okay, 1.96 probably sounds familiar to you guys already. This is coming from the normal distribution, where that encompasses the middle 95%. The standard error is p tilde times 1 minus p tilde over n plus 4. And well, anyway, we use that to create our confidence interval. So we're going to have 0.857 plus or minus 1.96 times all of this. So it's just a matter of crunching numbers here. So actually, I'm going to not use 0.857. I'm going to use the actual value of 72 over 84, which is expressed here, and I'm going to just use that using the answer key. Do 1 minus the answer divided by 84. Take the square root of that. So I have 1.96 times 0.0381. So I'm going to multiply that by 1.96. And I get 0.075. Okay, so 0.857 plus 0.075, 0.932, and on the lower end, 0.782. And so we would say, I am 95% confident that the population of nurses, RNs, is between 0.782 or 78.2% and 0.932 female. So between 78% and 93% female, essentially. Okay, and we would say that. All right, we're just going to learn the 95% confidence interval for P based on P tilde. If you wanted to change the confidence level from 95% to something else, it's not as simple as just changing this 1.96. You actually have to change the way you calculate your Wilson adjusted sample proportion, and it just gets too messy. Or it's not that messy, but for a method that I feel is less commonly used, we probably don't need to go into less commonly used confidence intervals for a less commonly used method. So we'll just say 95% confidence interval using P tilde. Okay. All right. So we'll stop